We have proved De Moivre's theorem, which states that cos theta plus iota sin theta raised to power n is equal to cos n theta plus iota sin n theta. Now we have the following properties. First, if n is any rational number, that is n belong to Q, then cos n theta plus iota sin n theta is one of the values of cos theta plus iota sin theta raised to power n. Second, if cos theta 1 plus iota sin theta 1 into cos theta 2 plus iota sin theta 2 into cos theta 3 plus iota sin theta 3, so on, we multiply it with cos theta n plus iota sin theta n, we get it equal to e raised to power iota theta 1 into e raised to power iota theta 2 into e raised to power iota theta 3, so on up to e raised to power iota theta n, which becomes e raised to power iota bracket theta 1 plus theta 2 plus theta 3 plus so on up to theta n, which can be clubbed into cos of theta 1 plus theta 2 plus theta n plus iota sine of theta 1 plus theta 2 plus so on up to theta n. This is the most important application of De Moivre's theorem. Then, third, if cos theta minus iota sine theta raised to power n, we have to bring it into De Moivre's form. That is, cos theta will be replaced by cos of minus theta, minus sine theta will be replaced by sine of minus theta. So it becomes cos of minus theta plus iota sine of minus theta whole raised to power n. Now we can use the De Moivre's theorem. Therefore it becomes cos of n times minus theta plus iota sine of n times minus theta, which becomes cos of n theta, because cos minus theta is equal to cos theta, and minus iota sine n theta, because sine of minus theta is equal to minus sine n theta. Fourth, if we have cos theta plus iota sine theta raised to power minus n, we can use De Moivre's theorem. That becomes cos of minus n theta plus iota sine of minus n theta. Again that becomes cos of n theta minus iota sine n theta. Fifth, if we have cos sine theta plus iota cos theta raised to power n, which is not of De Moivre's form, we change it into De Moivre's form, that is, real part should be cosine of some angle, imaginary part should be sine of some angle. Therefore we change sine theta into cos of pi by 2 minus theta, and cos theta as sine of pi by 2 minus theta. Therefore it becomes cos of pi by 2 minus theta plus iota sine of pi by 2 minus theta whole raised to power n. Now we can use De Moivre's theorem. It becomes cos of n times pi by 2 minus theta plus iota sine of n times pi by 2 minus theta. Thus states the formula. Next we can extract roots of a complex number. Suppose z is equal to a plus iota b, a is equal to r cos theta and b is equal to r sin theta. We change it in terms of polar form. That is, r times cos theta plus iota sin theta. We know where r is equal to modulus of z, that is square root of a square plus b square, and theta is equal to tangent inverse b by a. In order to find out 1 by or qth root of z, that is z raised to power 1 by q, it becomes r times cos theta plus iota sin theta raised to power 1 upon q. Pulling out r, you get r raised to power 1 by q into cos theta plus iota sin theta raised to power 1 by q, where q is any natural number. Here what we do here, we first of all generalize cos theta plus iota sin theta. That is, theta is replaced by 2n pi plus theta, because cos theta and sin theta are parametric functions of period 2 pi. Therefore cos theta is equal to cos of 2n pi plus theta, and sin theta is also equal to sin of 2n pi plus theta. This becomes r raised to power 1 upon q into cos of 2n pi plus theta plus iota sine of 2n pi plus theta whole raised to power 1 by q. Using de Moivre's theorem, we get r raised to power 1 upon q times cos of 2 and pi plus theta upon q plus iota sine of 2 and pi plus theta upon q, where n can take the values from 0 to q minus 1, which gives us exactly q roots which are different. But if you put back again n equal to q, we'll get the same roots once again. Therefore, there is no need to put more values of n.